So we're on to a new exciting unit that will carry us through the rest of the semester. What we've done so far, I hate to tell you at this point, is not what I really think is chemistry. We looked at some tools we need to talk about chemistry in the early chapters, but for me, chemistry is the study of matter so that we can make predictions about behavior based on the structure of the matter. We're going to start in this unit tiny subatomic particles, put them together into atoms, put the atoms together into molecules and ionic compounds, and then finally look at collections of many molecules and see what their real-world properties will be. But we have to start somewhere, so let's go back to our story of the atom. We have already gotten as far as the Rutherford model of the atom, in which we had the protons and neutrons in the nucleus and the electrons moving around in the space outside. But we haven't talked yet about how the electrons are moving. So we're going to pick up the story there, and we're going to refine our model to keep up with better and newer experimental results. The challenge with studying atoms is that they're so tiny. We can't see them directly. So the strategy is going to be that we're going to probe the atoms by shining electromagnetic radiation or light on them. And we'll see what we can infer from that. So, a little bit about the nature of light before we can do that. When I say light, that's kind of slang. The proper name is electromagnetic energy, and you've probably heard in science class that light behaves as if it's made up of waves. So let's review some terminology for waves. I've got various waves on the picture here, and one quantity that you see labeled on them is this little Greek letter lambda. Lambda stands for the wavelength, and the only reason it's got a Greek letter to label it is that we don't have enough English letters to label things. So it's a letter like any other letter, it's just a Greek letter. The wavelength is the distance from a point on one wavefront to an identical point on the next wavefront. You can go from crest to crest, as I've shown you here. You can go from trough to trough. The wavelength will be the same. Another quantity that's useful to look at is the amplitude, and that's what they've labeled as A here. The amplitude is the height of the wave, so it's like it's oscillating around this midpoint. The amplitude is the height from that midpoint to the crest, or similarly to the trough. So we've got two waves here, and they've got two different amplitudes. They've got two different heights. A third important quantity related to waves can't be marked on the picture because it's not a distance. We're going to look at the frequency. And we have a Greek letter for that as well. That is the Greek letter nu, and in my word processing font, it looks like that. When I write it by hand, it'd be kind of a curved back like that. That's the Greek letter nu. Now, the physicists, in their eminent good sense, call frequency F, bless their hearts. The chemists call it nu. But what it is a measure of how frequently the wavefront repeats. It's the number of cycles per unit time. And now let's look at the units of these quantities. The wavelength is a distance, so the SI unit for wavelength is a meter. For frequency, it's the number per unit time, and in SI that's seconds. So that's 1 over seconds, or I could say seconds to the -1. You remember what a negative exponent means. It means 1 over that. Or you can call it hertz. I won't call it hertz because then I won't be able to use my good old SI units as I carry things through. There is a relationship between frequency and wavelength, and units are going to help me figure it out. So in this expression at the bottom, there's your wavelength lambda and your frequency nu. The units then are the units of wavelength times the units of frequency, or meters per second. Hey, that's the units for velocity, and that's what the v is in the equation. That's the velocity. Now, if I looked at a variety of waves, they could all have different velocities, but we're looking at a particular kind of wave, electromagnetic energy, or light. And light has only one velocity. For electromagnetic radiation, the velocity is the speed of light, which we call c. The speed of light in a vacuum is a constant, and I'll let you know what that is. I'll always give you the value. That's 2.998 times 10 to the 8th meters per second. You remember, we've got this agreement. We don't memorize things. Whenever you need to know a physical constant, I will give you that data, just like I always give you Avogadro's number. We think here, we don't memorize. We are also getting into material that has more complicated equations than dimensional analysis can do. So whenever you see an equation in a red box, I will provide that equation along with the physical constants at the tops of your quizzes and tests and things like that. I hope I proved to you on the previous slide I don't need to do that. You probably could figure out that equation from the units for frequency and wavelength. However, I want to play fair here. I will give you the equation and I will give you the value of the physical constants, but I will not tell you the meaning of the symbols. So it's your job to know what the equation applies to and what the symbols mean. This is an equation that relates the wavelength to the frequency of light. We will do some calculations with that soon, but before we use an equation, I want to have a gut feeling for what that equation is telling me. What that tells me, because the speed of light is a constant, is that the wavelength and frequency are inversely proportional. That is, the wavelength is inversely proportional to the frequency. As one gets bigger, the other gets smaller. So now I can use that to show you this electromagnetic spectrum, which shows the different kinds of electromagnetic radiation. All that differs from one kind to another is the wavelength and frequency of the light. So down here, I've got a scale. On that axis, we're measuring wavelength in meters, and you can see that the wavelength gets bigger to the right. That's what the scheme at the top of the diagram says, is that wavelength increases to the right. I like the little schematic here. They're also showing here that the wavelength increases to the right. Now, we've got frequency as well. And we saw from the equation at the top of the slide that frequency and wavelength are inversely proportional. So although wavelength increases to the right, frequency increases to the left. Or in other words, the frequency decreases as we go further to the right. Now, just for fun, visible light is just one small part of the electromagnetic spectrum. And if you want to win a trivia challenge, do you know the way to remember the colors of the rainbow? I was taught Roy G. Biv just for fun. And you can see red, orange, yellow, green, blue, indigo, and violet. Somebody always asks me, what's this indigo? What's the difference between blue and violet? Now, in this continuous range of colors, who knows where one color stops and another one starts? The story I was told is that indigo was introduced into the scheme by someone who studied music. And they wanted 7 colors in the rainbow to match the 7 notes before it repeats in music as an octave. So that's just a story for what it's worth. So we've seen that electromagnetic radiation, light, behaves as if it's made up of waves. And up until the year 1900, wave mechanics explained the experimental results that we saw. But since then, the advances in physics have meant that we've had to update our theory a little bit. Let's see what else we need to know about light. Back in the early 1900s, the discipline of quantum mechanics started, and it deals with quanta, or little packets of energy. The basic idea is that energy behaves not only as if it's made of waves, as we've discussed already, but simultaneously light energy behaves as it's made up of particles or packets or quanta. So we talk about photons now. That's a quantum or a particle of electromagnetic radiation. A particle of light. So what they say is that light has particle-wave duality. In some experiments, it behaves as if it's made up of particles, called photons. And in other experiments, it behaves as if it's made up of waves. We're going to need a little bit of math to relate the particle model to the wave model we were looking at previously. And that relationship is the next equation that you see in the red box, which means, of course, I'll always provide it to you. Your job is to know what it means. That E stands for the energy of a photon. The energy of a particle of light. This is an equation for the energy of a particle of light. E equals h nu. That's your good friend frequency again. And what I can see from this equation is that the bigger the frequency of the light, the more energy the photon has. They're directly proportional. The other variable in the equation is h, and that's just a proportionality constant to make the equation true. It's called Planck's constant. And I'll always give you the value. It's 6.626 times 10 to the negative 34 joule seconds. That's joules times seconds. That's not joules per second. Why does it have those units? Those are the units it needs to make the equation work out. We'll use this equation in calculation soon as well. But what I want to show you before you do that, again, is a gut feeling for that equation. So I've got 3 pictures of waves here, which I will label A, B, and C. And I'm going to ask you some questions. If you can answer these questions, you've got what I wanted you to get from this video so far. Which one of the waves, A, B, or C, has the greatest wavelength? That's A, right? And I can see the longer wavelength for A and a much shorter wavelength for C. All right, next question. Which wave has the greatest frequency? C has the greatest frequency. It repeats most frequently. So you can see, as we saw in the earlier equation, that wavelength and frequency are inversely proportional. A has the biggest wavelength and the smallest frequency. All right, let's add in the energy of a photon. Which one of these waves corresponds to a photon of greatest energy? That would be C, because we said that the one with the highest frequency has the highest energy. And I can go back and show you our electromagnetic spectrum. We also had energy on that schematic at the top. So energy increases to the left just like frequency increases to the left, whereas wavelength increased to the right. Okay, so we've done a good study of light. Now let's see what that has to do with probing atoms. I wish you were with me together in class. I would show this to you in person if I could, but instead I've put a link to a video on our Moodle page, and some other teacher is showing you exactly the same lamp I would show you if we were here together. What the setup is that you've got a light source, some lamp, and here's what's called a diffraction grating. It's just a little slit there. You could use a prism as well. And you know that if you put light through a prism, and you'll also see if you put it through a diffraction grating, or here, this is a slit, this isn't actually a diffraction grating, you can bend the white light into its various colors. Now this shows a continuous spectrum from an incandescent white light. I don't know if you guys have even seen incandescent bulbs before. Those were normal when I was a kid, but we've all switched to energy-saving bulbs now. This lamp, though, provides what's called a line spectrum. We only see certain colors, certain lines, instead of the whole thing. Now we'll see that this line spectrum is produced because of the atoms that are in the lamp. So we're going to keep our mind open for two explanations. Why do I get lines instead of a continuous spectrum? And we'll also see that the lines are in different positions for different gases. What is that telling us? Here's a picture of the spectra that you would get from various lamps. So the one on the top there is a continuous spectrum from an incandescent light, or if you held a prism up and looked at sunlight through a prism or a diffraction grating, it would be a continuous spectrum. The important atom in our story is going to be hydrogen. Hydrogen gives particular lines. Here's a red one, and in most pictures, that looks greener than that does. It's on the edge of blue-green. And there's blue, and there's violet. So why, now this would be produced by a lamp, just like the one you're going to see in the video on the Moodle page. It has a very low pressure of hydrogen gas inside the lamp. We're giving electrical energy when we turn the lamp on. That energy is given to the hydrogen atoms, and the hydrogen atoms produce these very particular lines, and these lines only. If I weren't looking through a diffraction grating, the light from a hydrogen lamp would look kind of purple. And that makes sense when I look at the line. There's blue and violet and a kind of a blue-green together. That's predominantly going to give purple when those colors are all blended together. Different atoms give different colors, though. If you look at sodium, if I had a lamp that had a very low pressure of sodium atoms, sodium metal in it, I would get different lines. And the predominant color for sodium lamps is yellow. Sodium lamps you can get on headlights for your car, or sometimes street lights are sodium lamps, and they give a nice yellow color that cuts through the fog very nicely. Another lamp you're used to seeing like this is a neon light. A neon light is just a discharge lamp like I've been talking about. And when you look at it straight on without spreading the light into its line spectrum, it looks orange. But if we had a spectrum here, I would see a lot of lines in the orange and red part of the spectrum. That's what the light from a neon light looks like. So let's make a few points about what I'm seeing here. What I'm going to do is plug these lamps in, give them some electrical energy, and that's going to make what we call excited gas atoms. The law of conservation of energy says that the energy that comes from the electricity has to go somewhere. It goes into the atoms, and these atoms do something. They become excited. They end up at higher energy. But nothing likes to stay in a high energy state. Everything wants to go to a low energy state, like me on the couch after dinner. So after we excite the gas atoms, then they're going to release that energy again. They release energy in the form of light. And they give only characteristic colors. The key thing I want you to get from this, this is not an experiment, you didn't do it, but here's the data from somebody else's experiment, is that only certain wavelengths are observed. Only certain colors, only certain wavelengths, only certain energies are observed. So we're following the story like good scientists. The data comes first. We don't yet have a model to explain why this happens, but to get an accepted model for the atom, we're going to have to come up with a theory that explains these observations. Stay tuned for that in the next video.